Yes, hello everyone. Thanks for Hexacon for having us here, and thank you for attending our talk. Let's discuss how to attack the Android Bluetooth stack. So first, I'm Etienne, this is Mehdi, and we are both security researchers at Synactive. So, why Bluetooth? Bluetooth has always been an attacker's targeted choice. It's running on all mobile devices, basically, and for some reasons, it's always on most of the time, which makes it proximity zero-click attack surface. So this is very cool. It has room for a lot of vulnerabilities, as was demonstrated earlier this year by in the excellent presentation by Android red teams, where they presented multiple memory corruptions in Fluorid's Bluetooth stack at OffensiveCon. And in this presentation, we'll show how a full exploit could be developed out of it to get some remote shells. So the presentation will be outlined as follows. First, I will give a quick intro to the Bluetooth stacks. Then I'll go into the bugs that we'll be exploiting, and I'll give some exploitation primitives that we'll need to build the exploit. And then I'll let Mehdi show you how to actually get code execution on both Jemalloc and Scudo devices. So the Bluetooth stack looks like this. It's split in two main parts. On the lower side, you can see the controller part, which is what runs actually in the Bluetooth chip. For now, we'll just need to understand that it manages the establishment and the management of physical and logical transport. And in this presentation, we'll be talking about ACL a bit, which is the asynchronous transport, which carries most of the data frames. The controller part is linked to the host part through the HCI protocol. And the host part is the part that is running on your operating system. So for instance, if you use Linux, it's the BlueZ stack that runs in the kernel. If you use Windows and iOS, they have their own implementation. And in Fluorid, in Android, their implementation is dubbed Fluorid, and it runs as a user-land service. So on the host stack, as you can see, there is a bit more complexity. So we have here the L2CAP transport, and on top of this, multiple Bluetooth services that are used, for instance, to implement network sharing, human interaction devices, media streaming, and all the features that we know. Last thing I want to show in this slide is that, as you can see, some of the Bluetooth services, they require the peer to be authenticated before accessing it. And some of them are accessible prior to any authentication. But as we'll see, this distinction does not make much sense, actually. Just a few words about the kind of tooling that we are using. So to conduct this research, we built our own framework. Originally, we based it on the Blueborn's exploit code. It uses Scapy to build and parse Python HCI frames. And so basically what we've done is that all of the host part all of the host stack we re-implemented ourselves. And so we've built some simple implementation for L2CAP, ERTM channels, and all the features that we need to build our exploits. So as you can see in the example, with just a few lines of Python, you can establish a connection to peer, connect to some Bluetooth service, send a query, receive the reply, and yes, it's very convenient to experiment and try IDs on Bluetooth stacks. So, as I said, authentication is a bit of an issue when going to Bluetooth. So we've seen that multiple services require authentication. So usually, when you want to authenticate to a Bluetooth device, you will go through a pairing phase where you will have to manually verify a PIN code. But there are many different methods to do authentication in Bluetooth, and they do not all provide the same level of security. Some are considered to be man-in-the-middle resistant, while some aren't. And also, host stacks can add their own security measures. For instance, in Android, they have their own ACL management for paired device. For instance, if some device want to access some sensitive features such as SMS, contact, or so on, the user will be notified, and he will have to manually authorize the device to access this feature, and this authorization will be kept in the ACL for this pair. In the Fluorid stack, authentication looks a bit like this. So on the top, I show the prototype of the function that is used whenever Fluorid starts, and it's a function that's used to register a service in the Bluetooth stack. And the last argument of it is the security level that is required for a peer to connect to this service. And on the lower example, we can see that for the BNAP service, the peer must use a connection that is both authenticated and encrypted. And this is the case for most of the Bluetooth services that we've seen on the stack slide. But actually, there is a method. As I said, there are many different methods for authentication in Bluetooth. And yes, they prefer a bit usability over security. And as you know, you do not always go through these pairing files with manual PIN verification. So for instance, if you connect some Bluetooth headset to your phone, there is no actual PIN verification most of the time. So for this method, actually there is an authentication method in the Bluetooth specification that's called just work. And as its name says, it just works without any annoying security. So, and the fun thing is that we can actually use it to authenticate to Fluorid, and the user will not be notified. No interaction will be required. So we'll be able to access most of the services that we've seen, and this will greatly expand the attack surface that is available, and also the code that we can reach to build useful exploitation primitives. Just work comes with some shortcomings. For instance, you can't use it to impersonate an existing paired device. So if you use this method to authenticate with the same Bluetooth address as an already paired device, Fluorid will revoke all the ACL that were already provided to this device. And also, actually, some of the services will require the peer to have better security. So, for instance, some of the services will require the peer to authenticate with an authentication method that is man-in-the-middle resistant. Now, let's take a look at the bugs that we'll be exploiting. So, to summarize, it was a bug that was fixed back in 2023. It was a heap overflow in the GATT server. With just work, it was accessible without any authentication or user notification. And yes, we'll see that it's an integer overflow that leads to a huge, almost wild memcopy in the heap. So what is the GATT server? Basically, it's just a simple service that is provided by Bluetooth and allow a client and the server to exchange arbitrary attributes, so key pair attributes. The key is a 16-bit handle, and the value can consist of arbitrary data, usually quite short. And the vulnerability is in the command that is used to query multiple attribute values at the time. So the client will build a request that consists first of an opcode, the read multivar request, followed by the list of the 16-bit handles of the attributes that he wants to query. And then the server will have to build this reply with the reply to read the multivar opcode, followed by the attributes values, all prefixed by their 16-bit length. So this is the start of the function that builds the reply in Fluorid. So the first thing you want to look at is the declaration of the variables. those indexes and length variables. As you can see, they are declared as 16-bit unsigned integers. And then the second thing that we can see is the allocation of the reply buffer, which will be sized to contain the Bluetooth header, and then mostly the size of the MTBU that was configured when connecting to the service. So the client mostly control the MTU that is used, and so the size of the reply buffer. Yes, there were another vulnerability on line 0, but this is not the one that we'll be exploiting today. The vulnerability that we are going to exploit is the one that is in the loop that is used to append value to the reply buffer. And this loop is called on each attribute that must be appended to the reply. So the first thing that it does is compute the total space that is required to contain the attribute values that were previously added to the reply, plus the next attribute value to add. Then it adds 2 bytes, because it needs 2 bytes to encode the length. And then it enters this condition where it will try to handle the case where the total length that is required exceeds the reply buffer capacity. So it will compute this length variable, which will be cropped length. So it will try to crop the attribute value to just copy the part that fits in the reply buffer. And to do so, it will compute the attribute value length minus what would exceed the reply buffer capacity. The problem is that the computation at 3 is flawed because it does not account for the 2 bytes that were added for encoding the length. So by carefully crafting the query and configuring the MTU accordingly, you can have the length variable set to a -1 or 2, and it will be casted as an unsigned 16-bit integer, which will actually lead to a mem copy of 64 kilobytes approximately. So it will cause a massive heap overflow in both directions, because the source buffer will always be the attribute value buffer, which is allocated on the heap and is always about 600 bytes long. This one, we do not control it because with just work authentication, we can set arbitrary GATT values, but anyway, it will copy 64 kilobytes. So we do not care that much about the first 600 bytes. So just assume it's 0. And the destination buffer will be the heap buffer of the reply, where we mostly control the size because we can configure it by setting the MTU as we want. Yes, it is a bit messy for a primitive, but as we'll see, it's good enough to get code execution. So yes, the quick recap. We have this mem copy. We do not control the source, but we do not care because the source is only 600 bytes and will be copying 64 kilobytes. And the destination will be some malloc buffer where we more or less control the size. And yes, there will be a huge heap overflow in both the read and write directions. So to exploit it, we will need some good exploitation primitive. And to start with, we'll need some good heap shaping primitives. And the first thing that we might want to do is control the memory that will be the source of the mem copy. And to do so, we want to do some heap spraying. We want to put some arbitrary data behind this source buffer. And also, yes, we'll need some primitives to somehow shape the destination heap so that we can control its layout and put some interesting object in this. The thing is that exploiting the fluid stack, heap overflow in the fluid stack, it's not that easy. Especially the spraying part is quite challenging because there are not so many persistent memory allocations in fluid. The interesting packet memory allocations are mostly packet buffers. They can contain arbitrary data, and we can more or less control their size often. But typically, they are very short-lived. When a packet is received, it will be processed and then freed right after. And same thing when a reply is sent to the peer. Once it's transmitted, it will be freed right away. So the solution that we found is to force the packet allocation to become persistent. And the feature that we used to do so is to take advantage of ACL congestion. So ACL congestion is a control flow feature that is on the ACL layer, as we've seen. It's offered by the Bluetooth specification, and this is a feature that is normally only enabled at controller's level. So this is the controller decision to toggle this state. And basically, what it does is that it's used to reduce the flow of incoming ACL packets to avoid exhausting the internal packet buffer memory of the Bluetooth controller. So normally, it's a feature that is only toggled by the controller itself. But luckily for us, we are doing this research on Cypress Bluetooth controller, and there is a vendor specific HCI command that we can use to toggle this state. And the thing is that under congestion, we say that we can't receive, but we are still able to send commands, to send packets, I mean. So it will look like something like this. The attacker will advertise that it can't receive at the moment. Then we'll try to send many Bluetooth packets containing commands. When these commands will be handled by Fluorid, it will allocate a reply to send it to us. We'll try to choose commands that will trigger the allocation of control size and control data, preferably. And because we said that we are congested, at some point Fluorid will realize that he can't send these replies to us, and it will start accumulating them in memory, and we will have our spraying primitive. So as I said, Fluorid gracefully handles ACL congestion. As soon as it will notice that we are congested, it will stop sending us the replies, and simply accumulate them into a queue and wait for the congestion to be resolved before sending them. There is a quota on the number of messages that we can't queue this way on most of the channels, all of the channels, I think, but on the signaling channel that is used to establish connections to services and so on, there is no quota at all. So this means that we can, this way, spray as much memory as we want, infinite amount. And also to free all this memory, we can simply close the ACL connection, and they will all be freed at once. The last thing that we need for our spraying primitive are those packets that we can send and that will trigger a controlled allocation, control replies. The one that we picked is a configuration packet to configure L2CAP channels. And if we send invalid configuration options, this will trigger replies that are called config rejection, and basically this reply will contain the option that was just rejected, and as you can see, the allocation has a control size, and then it will copy in it the rejected option. So this is what we use to spray arbitrary memory. Now that we know how to spray the heap, we'll need better shaping primitive. We'll need some more precise primitives, so allocation where we can precisely control their lifetime, so we can individually allocate them, freeze them, and so on. And preferably, we want objects that we can use to build read and write primitives and build our exploit. And that's where ERTM mode comes handy. ERTM mode is another layer that comes on top of L2 cap, and it adds some reliability to it. So for instance, sequence numbering, acknowledgement, retransmissions, and we can abuse it in two ways to force persistent allocation. Actually, we can use it in two ways, in the two ways of the communication. So if we transmit, for instance, an ERTM fragment with an unexpected sequence number, so let's say we send a fragment with a sequence number of 1 without first sending the fragment with a sequence number of 0, this fragment will be kept in memory until the missing fragment comes. So this gives us a persistent allocation of both control size and data. And in the other way of the direction, we can do quite the same thing. We will somehow force Fluid to send us one ERTM fragment. Will not acknowledge it. So it will stay in memory forever as long as we do not acknowledge it. And the cool thing is that we can at any time request for the retransmission of this fragment. That will come useful later. So there are some limitations on ERTM mode. We can't allocate as many packets as we want this way. Only up to 10 messages can be allocated by L2 cap channel. Else, we would have used this mechanism for heap spraying in the first place. And also, it only happened on authenticated channels, but as we said, if you use just work, you can actually exert this feature. Before I go into the read and write primitives that we'll be using, I need to show you how Bluetooth packets are structured in Fluid. So we've seen this BT-HDR structure being used to hold the reply of the GATT server and the config request. Actually, it's used everywhere to represent Bluetooth packets. It is quite simple, as you can see. It has this header and of a fixed size, and then some variable length, variable sized data. The length field indicates the size of the data array, and the offset indicates the position of the current data according to the context of the processing. The nice thing about this structure is that it has no pointer in it. So if you can somehow rewrite it, it's easy to forge a valid one, even though you do not have a leak in the first place. So let's see how to build a relative read primitive. It's not that complicated. We will, as I said, force Fluid to send us an ERTM fragment on some ERTM channel, and will not acknowledge it, so it will stay in memory. Then we can trigger the bug to rewrite this ERTM fragment and control all of its fields. We can send, for instance, a large length and offset to our need to point somewhere further in the heap. And finally, we can request for the retransmission of this fragment. And if everything goes right, we will get the forged packet, and we will be able to leak some heap data up to 64 kilobytes if we set a very large length. The thing that we need here is I said we need to force Fluid to send us one ERTM fragment. There are not so many places in the stack where you can force the emission of an ERTM fragment with a somehow controlled size. And the way that we used is to use the AVCTP browsing channel and more precisely the get folder items. The get folder items is a packet that is used to retrieve the metadata of the song that is currently playing. So for instance, when you are playing some music on your car, this is what is used to display the name of the artist, the song name, and so on. And by carefully crafting a request for the get folder item, we can trigger the emission of an ERTM fragment of a control size. There are some default values that we can query, so we can craft we can have this controlled ERTM fragment the same way on many Android devices. Now for the relative heap write primitive, it will be even simpler actually. The first thing is that we will ourselves send an ERTM fragment to Fluid on some ERTM channel. Then we will, as I said, yes, we send an ERTM fragment with an unexpected, an incomplete ERTM fragment, so it will stay in memory for now. Then we will use the bug to control the contents of this fragment and to set offset and length according to where we want to write. And then we will send the following fragment, and it will be appended with this piece of code, and it will write our arbitrary data where we want further in the heap. So now the last thing that we need is a nice target object that we can allocate in the heap, and that we can first leak using the relative read primitive, then rewrite using the write primitive to leak the ASLR and then get code execution. So the one that we picked is a callback object. So Fluid use a lot of callback objects. They are provided by libchrome, and they are used to trigger function call upon certain events, and they contain multiple function pointers. They are callbacks, and the one that we use is the SDP discovery callback. It's a good candidate because we can precisely control its life cycle. So we can allocate it by simply establishing an AV RCP connection, and also we can trigger its execution by simply closing the related SDP connection. And the nice thing about this callback is that it not only contains the function pointer that will be called, but also some of the arguments that will be passed to the function call. And the last nice thing about this callback is that it has heap references. If we leak the content of this callback, we will get some heap addresses that will be useful in the rest of the exploitation. So now I will let Mehdi show you how to use these primitives to actually get code execution.
Yeah. Thank you, Etienne. Now we'll see how we will use this primitive to get code execution on Jemalloc devices and also on Scudo devices, and we'll start with Jemalloc. So as Etienne mentioned, the vulnerability allows to overflow 64 kilobytes of heap data, and in order to overflow a target object with control data, we need to shape the source of the overflow. And for that, we adopted the following strategy. So the first step is to enable the ACL congestion so that we can spray a lot of configuration injection messages that contain our control data. And during the spray, we'll also interleave the allocation of a couple of ERTM messages in order to create holes in the heap. Then we'll disable the ACL congestion. This will cause the releasing of all of configuration injection message, but our control data are still present in the heap. And then the last step is to free the ERTM allocation by closing, for example, the related ERTM channel, and this so that ERTM allocation will be reused by GATT-related object during the overflow. So our goal is to get the following heap state. So on the left, we have the heap state before disabling the congestion, and on the right, we have the heap state after disabling the congestion. So as you can see on the right, GATT attributes are reusing allocation previously detained by ERTM message. Each GATT attribute is followed by control data, and one of those GATT attributes will be the source of the overflow. Now, in the same way, we have to shape the destination heap. We would like to arrange our object, the reader and writer object, as shown on the figure in the right of this slide. So we'd like to get the reader and writer object reachable from the vulnerable object, and we also want to get the target, the callback object at a fixed offset from the writer object. And for that, we'll start, as usual, by enabling the ACL congestion so that we can spray configuration injection message. Then we'll create placeholder for reader and writer object by sending ERTM channel over a first gap channel. And then we will create a placeholder for the vulnerable object using, by sending an ERTM channel over a second gap channel. Then we'll close the first gap channel to release the placeholder and allocate immediately the reader and writer object using the ERTM message presented earlier by Etienne. And then we'll close the second gap channel and trigger immediately the overflow so that you can override the reader and writer object, and then allocate our callback, and this callback can be manipulated using our reader and writer primitives. So now how we can get code execution with this? So the first step is to shape the heap, the source and the destination as shown as explained in the previous slide. Then we'll trigger the overflow to corrupt the reader and writer object, and then we'll allocate our callback, the STP callback. Then we will use our read primitive to leak the content of this callback. So we'll ask the retransmission of the altered packet in the transmission queue to get the leak of the callback. And once we have the content of the callback, we can rewrite it using our writer primitive. This callback has a function pointer, so if we override this function pointer and trigger the callback, we get code execution. However, before getting code execution, we have to fix some minor issue here. The first one is that with this callback, the SDV callback, we do not have control over the third argument. And to fix that, we found this function that we call the gadget function. And this gadget function allows us to call an arbitrary function, and we control up to 5 arguments. So this is convenient for us to call mprotect, for example. Now the second issue is that this callback allows us to call a single function. I would like to call at least 2 functions. We want to call mprotect followed by a jump to our shellcode. So for that, we found a second function called the list clear function. This list clear function takes as input a list object, and this list object has 2 function pointers that are called when releasing a node inside this linked list. So if we craft a fake list object and inject it into memory, we can call several functions. But for that, we need to get controlled data at a known address. And to get controlled data at a known address, we have to go back to our callback. We can see in this callback has a reference to has a heap reference to a large object, 10,010 bytes. So the idea here is if we spray object with the same size and with controlled data just after the allocation of the callback, we can guess an address where we have our controlled data. Okay, now we have all we need to get code execution. So here this slide sums up the execution control flow. So we use our write primitive to override the function pointer inside the callback. We overwrite it with the gadget function. The gadget function allows us to call the list clear function with a fake list object shown in yellow here. And then this list function, this fake list object contains 2 function pointers that allows us to call mprotect and then to jump to our shellcode shown in blue. Okay, I think we have a demo here. So in this first video, we show our setup. No, didn't start, sorry. So in this video, we showed our setup. And as you can see, we use 2 Bluetooth controllers because at some point we need to enable the congestion with 1 controller and still interact with the target using the second controller. And also because we have a limitation on the number of ERTM channels that we can connect to. So with these 2 Bluetooth adapters, we can overcome this limitation. It survived to that. Okay, so in this second video, the actual exploit. So we will pay shots if the exploit doesn't work. Sorry, it worked, no shots. I think that's it for the demo. Yeah, actually it was hard to get code execution on Jemalloc devices, and honestly it was a nightmare to get the exploit working on Scudo. So before getting into the Scudo exploit, we'll briefly introduce this allocator. So Scudo is a hardened security allocator. It has 2 allocators. Here we'll focus on the primary allocator that serves allocations smaller than 10,000 bytes. And yeah, Scudo organizes memory into region. Each region is dedicated to allocation of a specific class size, and a region is sandwiched between two guard pages. And the region itself is divided into memory blocks, and a memory block consists of 16 bytes of metadata, followed by a memory chunk that is the actual memory returned to the program when calling malloc. Now, how memory allocation works. So when we make a call to malloc, the allocator will pick a chunk from the cache, and if the cache cannot fulfill this request, then we will refill the cache from the global free list. And this global free list contains transfer batches. A transfer batch is a group of pre-allocated memory blocks. Now, even if the global free list does not have any more transfer batch, then the allocator needs to create new transfer batch. So for that, it will allocate a memory from a region, splits this memory into memory blocks, shuffle the memory blocks, and then group them into transfer batches. And one of those transfer batches will be used to refill the cache. Now, hopefully, the memory shuffling mechanism is not applied to the entire region, but it's applied only per batch of memory blocks. And the number of randomized blocks depends on the class size. And for smaller allocation, this number is equal to 52, which is the product of the number of transfer batches per the number of memory blocks inside each transfer batch. So now with this observation, how we can make our target object reachable from the vulnerable object by bypassing the memory shuffling mechanism. So for that, we can simply separate the allocation of the target object from the allocation of the vulnerable object by inserting an allocation in between. Okay, checksum verification now. Yeah, as I said previously, Scudo prefixes a memory block with metadata, and the metadata contains a checksum. So if the checksum is corrupted, then the program will abort. So to avoid that, we have two options. The first one is to overflow only free chunk, or the second one is to only overflow persistent and controlled allocations. Okay, now the memory shuffling mechanism. Due to the memory shuffling mechanism, we cannot use anymore our relative write primitive, because the writer object expects the callback to be allocated at a fixed offset, and we cannot get that with randomized memory blocks. So we use this solution is to trigger the overflow twice. During the first overflow, we will try to overwrite a reader object to get a memory leak, and during the second overflow, we will try to overwrite a callback object to get code execution and hope to survive to 64 kilobytes of damaged heap data. Okay, so yeah, as usual, we need to shape the source of the overflow. So for that, we'll rely on the same techniques. We will enable the ACL congestion. We will also spray the heap with a lot of configuration rejection message, and also we'll use ERTM message to create holes in the heap. The only difference here is that we need to get our source of the overflow shown in green here, followed by a lot of configuration rejection message, so that we can reach the target object with control data. Now, yeah, during the memory leak, we unfortunately, despite our effort, we didn't manage to get the STP callback present constantly in the leak. However, we discovered that there is another callback called the capture callback that is always present in the leak. And this callback has all we need to proceed with the exploitation step. This callback has a heap reference, so that we can guess and address where we have controller data, and it also has a function pointer, so we can guess the base address of the Bluetooth library. However, during the execution step, we still use the SDP callback because we control the life cycle of this callback. So we control when this callback is allocated, and we control also when this callback is triggered. So it is convenient to use this one. However, the only problem here is that due to memory shuffling mechanism, we cannot overwrite all the fields of the SDP callback reliably. So, however, thanks to this gadget, we only need to overwrite two pointer of this callback object to divert the execution control flow. And the rest of the payload is exactly the same as the one used in the Jemalloc exploit. Okay. Now, once we have code execution, what we can do when achieving code execution. So our idea is to get a shell over Bluetooth. For that we implemented a basic protocol that runs over Bluetooth to run shell commands to send a file on the target device and so on. And we patched it, for that to work, we patched few functions of the Bluetooth stack that are handled receiving Bluetooth frames. And yeah, we also registered a signal handler to catch segfaults because at that point, Bluetooth wants to die and we keep it alive so we can interact with the target and send our commands. Yeah, time to conclude. So during this research, we tried with Etienne to play with one powerful vulnerability because this vulnerability does not require user interaction. It does not require authentication. However, it is not trivial to exploit. And yeah, we managed to exploit this vulnerability on Android devices. We tested this exploit on a Xiaomi device running with Jemalloc and also on a Samsung device running with Scudo. And yeah, the reliability is not quite good. But hopefully the Bluetooth process crashes and silently reboots in case of a failed exploit attempt, so we can keep trying again and again until we get a shell. And we conducted some basic tests, and it takes approximately 2 minutes to get a shell on the Jemalloc devices and up to 5 minutes to get the shell on the Scudo device. Yeah, the future now. Now the Gabaldor stack is the new Fluoride stack, is the new Bluetooth stack. It has enabled in Android 12 and is the default stack since Android 13. The Gabaldor stack is the rewrite of the Fluoride stack in Rust, and this work is still in progress. And yeah, the exploit is still working even if Gabaldor is enabled because as late of 2023, only the low-level layers of the Bluetooth stack has been rewritten in Rust, so this does not impact the vulnerability present in the GATT server written in C. Yeah, some few references here that helped us work on this research, and we would like to acknowledge Kevin Denis, who worked with us on this. I think that's it. Thank you all.